Hello, this is the next video in a playlist that I'm calling Complex Variables, where we're going to do a detailed playlist of complex analyses. But first we're covering complex numbers, and today's topic is the dot product and cross product of complex numbers. So first let's look at the definition. So that Z1 and Z2 be complex numbers. Now the dot product, sometimes called the scalar product of Z1 and Z2, is defined like this. So Z1 dot Z2 is the product of the moduluses, which we have a video earlier on the modulus of complex numbers, times the cosine of the angle created by these two vectors. Now the angle is between 0 and pi. Or it can be shown to be this product, the product of the x's plus the product of the y's, or the imaginary components, which is also the real component of this product between the conjugate of Z1 times Z2, which also in an earlier video we showed it can be this. Now the cross product of Z1 and Z2 is defined by this, Z1 cross Z2. Now instead of the cosine, we use the sine between the angles, and it can be shown to be this product, x1 times y2 minus y1 x2, which is also the imaginary component of this product, which we've showed in an earlier video, which is this. Now we're going to use these two pieces here first. So when the cross, or when the dot product is 0, that's a necessary and sufficient condition that Z1 and Z2 are perpendicular. And you can see that because the moduluses are always positive. So the only way that this number can be 0 is if the cosine of theta is 0, and theta is the angle between them, and that means it's a 90-degree angle. And property 2, the Z1 cross Z2 is 0, and that's a necessary and sufficient condition that Z1 and Z2 are parallel. And you can kind of see that here, since the modulus of Z1 and modulus of Z2 are always positive. The only way for this to be 0 is if the angle is either 0 or pi, which of course means that the two vectors are parallel. Now let's show that this product, so the conjugate of Z1 times Z2 is equal to this. And we're going to make use of this piece here and this piece here. So so we have a complex number, right? The conjugate makes it, keeps it a complex number, and the product of complex numbers is a complex number. So generically, you could say we have the real component of that number plus I times the imaginary component. But look here. So the real component is the moduluses times the cosine, and the imaginary is the product of moduluses times sine. So we can rewrite that, but we of course factored out this modulus. But then Euler's formula tells that's e to the I theta. So we're finished. That's what we wanted to show. Now the magnitude of the projection of Z1 onto Z2 is this. So the magnitude is, the length of the vector, or the modulus of that vector. And this is such a critical component in all of statistics, projecting something onto, a vector onto some other vector or column space. That's the whole concept of multiple linear regression. So this is an important component, and we'll revisit it in later videos. But let's look at a picture of what's going on first. We have two vectors, Z1 and Z2. And what we're doing is we're projecting Z1 onto Z2. And when you say we're projecting it, that always means at a 90-degree angle, which is called a perpendicular projection matrix. And that's linear regression, multiple linear regression. Now, there are what's called oblique projections. So you can take Z1 and project it obliquely onto Z2, and then you're jumping into what's called weighted least squares regression. But here we're just projecting it, so that's kind of a unwritten rule that it means perpendicular projection. Now, if we wanted to find this length of this red vector, the projection, we know the angle between Z1 and Z2, and we know the modulus of Z1. So if we take the cosine of theta, that's this length over the modulus, so you can kind of back solve for the length of that red vector. Now the magnitude, in this example, I don't know, I used to have numbers here, but I took them off. I probably should have taken that away. So the projection of Z1 onto Z2, so this is actually a vector. So without the absolute value or the modulus operator around it, that's actually the vector in the direction it points, but we want the magnitude of it. So as we said, it's the cosine of the angle times Z1, when you back solve for that. But if we multiply it by 1, Z2 over Z2, this top part is the dot product of Z1 and Z2, and that's the modulus. And that's what we wanted to show. Now the area of a parallelogram having sides 1 and 2 is the absolute value of the cross product of Z1 and Z2. So let's look at a picture of this. So we have two vectors, Z1 and Z2, and then you can think of it as creating a parallelogram. Now to find the area of a parallelogram, you find the height and take it times the base. And then that's the area of this parallelogram. So we need to know H. Now, as a reminder, we know the modulus of Z1, right? So if we take the sine of theta, that's H over the hypotenuse. So we can back solve for H, and then we know that value. And of course, we know the magnitude of the base, or the modulus of Z2. So then we're finished. So the area of this parallelogram is the base times the height. The base, of course, is just the modulus of Z2. And the height is a sine of theta Z1. But this is the definition of cross product. And of course, we want the absolute value in case it's negative, because this has to be a positive. Distance is positive. Now let's find the area of a triangle with vertices Z1, Z2, and Z3. So here's a picture of what we're trying to do. We have Z1, Z2, and Z3, and those can be anywhere in space. But then we connect the two or the three endpoints, and it creates a triangle. We want to find the area of this. Well, if we recreate like two vectors coming out of Z1 that points in the direction of Z2 and Z3, and of course that's this Z1, or Z2 minus Z1 is this vector, and Z3 minus Z1 is this vector. And now we have two vectors, and we can calculate the area of, say, a parallelogram with these two vectors. But then this triangle is really half of the parallelogram. So we just calculate the area of a parallelogram and divide it by 2, and that's the area of this triangle. And so that's what we do. We take these vectors and then calculate the area of a parallelogram. So Z1, Z2, and Z3 are just generic complex numbers. And we're going to call it Z4. So this would be Z4 and Z5. But it's the difference of the, oh, that should be Z. It's the Z2 and Z1. Dang it. And then in complex number form, it's this, right? The difference of the real components plus difference of the imaginary components. And Z5 would be Z3 and Z1, and that'll be fixed in the hard copy if you want to purchase this later. It's the difference of the reals plus the difference of the imaginary components. So the area of the parallelogram is this cross product between Z4 and Z5. Of course, we need to take the modulus of it, or the absolute value, because that could be negative, but we want it to be positive because of the area. Now, actually, some just say cross product, and then they put plus or minus a half out here, and they say, either multiply it by minus 1/2 or 1/2 to make it positive. But if you just take the absolute value of the cross product, that's the same thing. Now we showed that the cross product is equal to this, right? So we're using Z4 and Z5. That's X, that's why we have subscripts 4 and 5 here. But the way we defined it as the difference of the vectors, we plug in X4, right, which is the difference of the real components, difference of the imaginary components of vector 5. Same way here. Now, when you do the multiplication here and here, you get two terms that cancel, and then you're left with this. But it should be noted that this sum, or this, the product, the sum of the products, can be thought of as the determinant of this vectors, right? So these are our three vectors, then you put just ones out there and you take the determinant, you get this. But of course we need the modulus, which is this absolute value around it. And that's it. And so you can look up calculating the area of a triangle of 3 points, and it often gives this as the definition, but we just proved it. Okay, well, that's all I have for this video. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.